All right. So, from the very beginning of the quarter, we have been talking about how to, well, the whole purpose of this class is that how are we going to improve the performance of your application end to end, right? So in the past, a lot of courses that you learn is mostly focused on just a small component in your software. So and turns out that we lose the whole picture of what the program is doing, and turns out we also miss a lot of opportunities and really what's really influenced our performance. So if you think about from the very beginning, we have been talking about the workflow of an application. Typically, you have your source data stored on some data storage device, and those data storage device, they don't store data in a format that your application really wants. So it turns out you always have some kind of code in your program that try to deserialize your your data into some kind of data structures that your compute kernels can use. And then you use hardware accelerators to run those compute kernels and then generate the result. And hardware accelerator is only for compute kernels. So because the hardware accelerator reduces the time in compute kernels, so based on MDOS law, we know there are more other important things that we have to focus on. So we have been talking about in-memory processing to accelerate the code that's memory heavy. And then we also talk about in-storage processing in terms of the data that is that has to deal with large files. And the last time we talked about in-storage processing. And I also talk about my failure story about in-storage processing in a way that in-storage processing is something that's really difficult to make it work. Because if you think about the conventional model, there involve several components like the storage, media, and access. And in-storage processing model does not affect that part of latency or bandwidth, because that's essentially what you have to pay. So because the storage median access time is so long, so that's why the idea of active disks doesn't work. Because if you think about if the storage median access is the most significant part, and if it's already on a hard disk drive that's really slow, it's already like 10 to 5 or 10 to 6 times slower. So no matter how you apply in-storage processing model, it's not going to work out anyway. So that's why active disk, it sounds like a good idea, but it turns out it wasn't very popular at the time. And now, because we have the non-volatile memory, which reduce the latency of storage median access by a degree of 1,000 times. And also because the files that we are dealing with is way larger than what the files that we have to deal with in the past. So it turns out that the amount of time that we store in, we spend in storage is actually more significant than the past, giving in-storage processing model more opportunities to work out. And but even with in-storage processing model, there is still an overhead between the data exchange and your in-storage processing processor. And the benefit of doing this in storage is that by using more parallel channels, you can potentially improve the latency or the bandwidth between your in-storage processor and your storage medium. However, the reason why smart SSD manufactured by Samsung and Xilinx together is not a very successful product, because although in a paper, a research paper, they do have the advantage of having a coprocessor with more bandwidth available for the processor. However, in reality, their product does not do things in that way. Their product does not do things in that way. In fact, they separated the FPGA on the other side of a PCIe interconnect, and the bandwidth is not really larger than the external bandwidth. So making the real smart SSD commercialized product less ideal than their paper. So turns out if you cannot leverage a faster processor to reduce the ISP computation time, then turns out that, or if you cannot significantly reduce the data volume, so turns out you are going to get very limited effect. So if you want in-storage processing model to work, then this formula that I listed here, they have to be held. And for that to be held, several items that we have to pay attention to. First of all, the computation on the ISP cannot take too long, and we should significantly reduce the data volume. And also, the ISP processor must have efficient internal access to the device. If none of this is true, then this in-storage processing model won't work. So sometimes it seems like in-storage processing model is a good idea. However, if you consider there are 4 other factors that you have to consider, it's not a big surprise that you don't see a lot of applications of in-storage processing model, because it's really difficult to balance off this 4 perspectives. So this is the commercialized smart SSD product, and as you can see, although they use the so-called P2P communication, however, right now the issue is not about if you communicate with P2P. It's more about if you can leverage the bandwidth, make it larger than the one going to the host. If it's not, since CPU processor is faster, why don't we just use the CPU, right? Why are we leveraging the smaller and slower FPGA, right? So, and the last time, okay, so the last time, okay, I think that's not the right one. So the challenge of ISP is a lot. First of all, programming is still an issue. And the other thing is that because we have limitation on applications, so your application either has to have low compute intensity, or you have to reduce the volume significantly after pre-processing. And also, you have to make sure that the processor we have cannot, you have to know that the processor we have, they cannot be too powerful. All right, so before we start the lecture today, take a look of these pieces of a code. And can you tell me where do you expect the program to spend the most of time? And why? What do you guys think? Okay.
I think it's definitely BF-scan.
Okay. Why definitely be F-scan?
Because I have done like measurements on sort for a class before, so I know approximately how long it's gonna take for 100.
Okay, but do you know why?
Because it has to go from the disk to memory to, as opposed to sort, which can only work on something in memory.
So then you're saying F-scanf is slow because because of your data is on the storage, so that's why it is slow.
Or not that it's, well, yeah, it has to go from file, it has to bring the file into memory, and then it has to read it. It has to do all the file system stuff.
So what you meant to say is that, okay, so what if we don't put the file in storage? What if we have like a rent disk? Would that be faster? You don't know. Right, because what you said, right? From what you described, you said because of the file is on the disk, so it's slow. That's what you said, right? So from what you talk about, it sounds like you believe if we have a faster disk, that problem should be resolved.
Not necessarily.
Okay.
I was thinking more so the extra like latency involved with the memory hierarchy.
Okay, it's about memory hierarchy. Okay, so let's take a look of a demo, and let's see if that would change your mind. Okay, let me see. Okay, so let me do this. So here I have this program, and as usual, I can compile it, and let's see, right? And right now I generated a version, and I'm doing this, and it's currently putting on a hard drive, right? And I try to scan it and try to run a whole program. And as you can see, right, for this amount of data, like 100,000 records, indeed, it takes more time to scan. It takes 45 milliseconds to scan, 43 milliseconds to sort. So the scan, a lot of you think about it's an elder-n algorithm, and sort is like an n-log-n algorithm. So from the algorithm perspective, a lot of you might think about that the complexity go with the scan, so go with the sort, right? But the thing is that, okay, even though I give it smaller amount of values, right, it still take more time in scan than the sort, right? So the thing is that scan is more time consuming. So a lot of you might think, okay, it's more about which disk that I'm using. So right now what I'm doing is that I copy it to the /temp, which is an SSD, NVMe SSD backup the storage, right? And take a look. What do you get? The latency is still about the same, right? The scan latency is still taking more time than sorting, right? And complexity is still true in a way that if you scale it up to a certain degree, it will eventually go with the fact that sorting is going to take more time than scan, but scan is still more significant in this case, right? And again, another thing is that even though I use the solid state drive to store the data, the scan latency is still taking more time than well, the scan latency is still very significant, as you can see here, right? So this is on a hard drive. This is on a solid state drive, right? The scan latency is pretty much the same, right? So using a solid state drive doesn't help. Any idea why? Or what does that tell you?
So I have experienced that if I use certain file, I create it repeatedly. And I would say for the first time it's really slow.
Yes.
And the later times it's really speed up.
Right, but here I have already done it several times, right? So this is already the fastest version. But first of all, let's answer your question. Why the first time is slow?
So I think the first time is like actually from disk to memory.
Okay.
And operating system may have some organization that you store something in memory that I think you may think.
Okay, so the second time, right? Remember the last time we talked about page cache, right? And that's why we talk about why P2P is not a good idea. Because if you are going to reuse the same file again and again, if you use P2P, you are going to bypass the page cache from the operating system. However, if you go through the main memory, go through the manipulation of your operating system, the operating system will create a cache of your whole file in the memory, right? But like for this particular cases, do you think we have the file already in the memory? Yes or no?
Probably yes.
Probably yes, right? So this is pretty much answering what you said, right? Now, you pretty much have the whole file inside of memory. And you still get the speed that scanning is taking very significant amount of time. So with this experimental result, what's the insight behind this? Do you think storage median access time or the storage is the main bottleneck? Then if it's not storage, what's the main bottleneck?
Scan it.
Okay, but why is scan so slow?
IO-related stuff is always slow.
But if right now we are already cached in the memory, it's still IO related.
Maybe the cache, it caches the original file in the memory, and it maybe covers another data structure. Maybe that part.
Okay, so you said because there are memory copy.
Maybe.
What do you think?
I think it just has to do with actually taking data and then making it into like variables or assigning it, parsing it, because these files are all in binary, so it has to go interpret.
Okay, so first of all, right, a lot of cases, there is always one thing that we didn't pay attention to. is the format how you store data. So in fact, these days, people love to talk about open data, love to talk about big data, right? And there are a lot of open data projects that encourage people to learn things from the available data, right? And try to see if those things that can help us understand the whole world better. However, if you pay attention to the data formats that people want to use, right? Like you see these data formats every day, right? You must have the experience of dealing with JSON. You must have the experience of dealing with text. You must have the experience of dealing with CSV. If you do biological like informatics, you also FASTA data, right? Like I have done FASTA for quite a while, 10 years ago. And also like SVG it's a description language of graphics, right? So all of those are data formats that are frequently used. However, their encoding is, if you directly open these files, right? If you don't have like a JSON reader, if you don't have Excel, you can still look into the content of a CSV file or a JSON file, right? Because they are human readable format. So for all those human readable formats, they are encoded using ASCII code. So what does that mean by ASCII code? So if today I have this number, in ASCII code, they are indeed using 8 characters to store this A digit. So although visually, when you open a text editor, you are seeing this is a number. But in fact, on the storage, they are going to occupy actually for 9 bytes. And this 9 bytes, they are, and this, for the following hexadecimal strings, they are the encoding of this numbers. And this is the so-called Little Indian decoding, encoding. So that's why you see there are some flips in a number. So for example, if the first two characters are 1, 2, then it will go with like 31 and 32, right? And the 30 here, well, so in the ASCII code, your character 1 is in fact hex 30 plus 1, and 2 is hex 30 plus 2, and also like similarly like 34 33 and 35 36 and 37 38, and each of this 2 digit of a hex is essentially a byte, right? And at the end, to separate one number from another, we also have to attach like sometimes like a space or a null character at the end, right? So it turns out you will have 0A as a space, right? So this is a number that is human readable. But in fact, in storage, this A characters or this A digit number would take 8 plus 1 byte. However, this is not a format that we store in memory. And as many of you know, if we want to store numbers in memory, we will use binary encoding. And for this A digit number, it will actually be encoded in just 3 bytes, like this, in the most compact representation, right? So this is the binary encoding. And since the memory objects, they have all be in binary encoding, And the reason why a lot of open data, they are stored in ASCII format for a variety of reasons. And the most obvious reasons is because they want to make sure the release data is consistent with their original recording. So who verifies that? Human beings, right? So that's one reason they use ASCII code. And the other reason is because ASCII code is human readable. So anyone getting this ASCII code encoded data, they can easily design their own parser to digest the data format. So you don't need to make any assumption in what kind of format that the user computer would accept. For example, I just talked about the Little Indian encoding, right? And that's and that's even more a serious issue for binary in memory, because like there are still big Indian machines that exist. So you cannot assume that the user computer always use the same binary format. The binary format would change computer by computer. Binary format in memory would change computer by computer. But in terms of the serialized format, there's only one standard. That's called ASCII code, right? So turns out, if we want to process ASCII code, like the code that we show you, first of all, you have to use some function that buffers part of your file content or the whole file content. So for example, if it's page cache, then you can assume the whole file content is already loaded from the storage to DRAM. So for the second run for the program that I show you, even though the fscanf seems to spend more time than the sorting, however, at that time, if you run it for the second time, like Xiaopei, what you said, right? It's already in the system main memory. So at that point, even though you upgraded your storage device to something else, it's not going to improve anymore. And in fact, even though the file is completely on the storage, it's still not going to change the performance that much. And the reason is because now, if you consider what's going after, what you have to do is that you have to first figure out the range of a string. So you have to go through the buffer for a few more bytes to figure out how many characters that I need to split out as a binary number, as a binary field that I need to fill in my data structure. And this ASCII code, they don't directly convert to binary number. So we previously see, well, it's 31, 32, 30, 33, 34 seems to be pretty straightforward. However, it's not like that, right? Because if you want to convert this to 0xBC614E, right, it actually would take quite a few steps, which we can talk about later, right? But the thing is that you can, this is like a very simple programming question, right? As you can imagine, you need to figure out where in a position of this number is. So you have to, first of all, subtract like 0x30 from the number, from the ASCII code that you read, and then multiply it by, for example, 10 to the 6 or 10 to the 7 or 10 to the 8 in this case. And then put the result in a summation number, right? So it turns out it's not just subtraction. And the thing is that because you have to perform accumulation, so it's not parallelizable. It's not parallelizable, right? And after you parse that number, you have to put it into another data structure right? So that's why, first of all, you have to send it to the DRAM. And then you have to move it to the processor to parse that number. And then after you are done with that, you have to trigger another load store instruction to store it in a data structure if your data file is really large, right? So it turns out a lot of traffic is going on between the processor and main memory. And then when you really want to run your compute kernel, you have again to load part of the application data back, application object data back to the processor's register. And even worse, if you are going to use the GPU to sort or to process this data structure, like the previous code, we are actually using the GPU to sort the data, then you have to trigger another memory copy between your main memory and the GPU. So it turns out you can see there are a lot of traffic here, right? So this is actually not a very efficient processing model. And here's the experiment that I have done before. So this is a set of Rodinia benchmark applications, and as well as big data bench applications. And within these applications, 7 out of 10, they are GPU accelerated applications. And the vertical axis is the throughput of parsing input data. And these 3 different colors, they represent when I store data in different types of storage device. And here, I already clear the page cache. So it's already filtered out the case where data is all in the main memory. So if you take a look at that, you will see RAM drive, which means that I use the DRAM to store the file in the very beginning. So the only overhead that I'm suffering is probably the file system. And the blue one is the data on the SSD, and the orange one is data on the hard disk drive. And you can see there's very slight difference between these 3 different types of storage device. So what does that mean? That means if you store data in ASCII code, it doesn't really matter what kind of storage device you are using, because they are going to be really slow anyway. Because if you take a look at the throughput of the parsing input data, it's just 2 digits of megabyte per second. And consider the bandwidth we have on the DRAM is 5 digits of megabyte per second. And consider the bandwidth between NVMe and your host is 4 digits of megabyte per second. And even with the hard drive, you should have hundreds of megabyte per second. So if you use ASCII code, what does that mean? The overhead of parsing your data is the bottleneck, not the storage median access. So using ASCII code to store your data is actually a terrible idea in terms of performance. And even worse, a lot of people would say, okay, like the last time we talked about why GPU direct file system is not a popular idea. Here's another reason of why. You are not able to parallelize the data parsing using GPU. So it turns out those serialized data format, you still have to use CPU to parse your ASCII data. So what does that mean is that even though you have the capability of directly sending the whole file content to the GPU, however, if the file content is not something that your GPU can digest, then turns out you still have to go through the CPU and main memory assembly to make it binary object before the GPU can really digest the data. So in this way, even though you have perfect support of P2P, even though we make P2P a lot faster than CPU going through CPU and main memory, it's still useless. And surprisingly, in a world we have huge amount of data, they are encoded in a certain way that only CPU can parse it. So turns out the GPU direct becomes really useless, right? So that's another thing that I have learned when I'm doing that project. So it turns out, what have you learned? So first of all, parsing the input takes as long as the computation. And if you have a really optimized sort, it's going to be more time consuming in that. And the good put of parsing, as we show you, is way lower than the speed of the I/O device itself. So what that implies is that the bottleneck is not your I/O performance. So some of you saying that it's because of the I/O device is slow, it's because this is slow. No, it's because parsing is slow, right? So what really matters at this point is not where you store your data, is what format do you use to store your data. So a paper that I have published in ISCA 2016, we are trying to parse the data. We are trying to address this data parsing issue using in-storage processing. So again, we use the data center SSD, which I should brought you a sample next time. It's actually, I do have one in my office, is that there are abundant processor cycles that are wasted. And this paper is called Morpheus. So it's published in ISCA 2016. And the idea is this. Instead of using the host processor to parse the ASCII data, we decided that we use the SSD processor to parse the application objects, and then create the application objects inside the storage and send it to the DRAM directly. So if it's the GPU kernel needs that application object, we can also send it from the SSD to GPU directly. So that's the idea of Morpheus. So it's a very simple idea that we just use the SSD processor to parse the data. So what's the benefit of doing that? First of all, it makes P2P more useful. So you can consider, like previously I said, I have done research in using GPU direct communication between SSD and GPU. And then I immediately figure out that a lot of applications, they doesn't work. So this actually is a follow-up paper of that, okay, how can we make P2P more useful? So it turns out here's a solution, right? So the problem is clear, right? We have P2P support, but P2P is useless in most of the cases because we still need a CPU to parse the data. So to solve the problem, we decided to use ISP. And the other thing is, one thing that you might caught me with a logic flow is that parsing, as we talk about, is actually compute intensive. Parsing is actually compute intensive, right? So if you check, wait, I should have a slide for that. Let me double check. If you check, if you check the compute intensity of parsing, okay, right here. Okay, if you check the arithmetic intensity of parsing, it's pretty much doing this, right? If you want to parse a character to integer, here's probably the code that you are going to write, right? So first of all, you have to have a loop that consistently scan your buffer until you reach a separator which is probably a null or something like a space. And then for each number, how to create a binary number? You have to multiply the accumulated value by 10 and plus the current string value minus 48, which is 0x30, right? And then this is how you convert a number, right? So if you consider this, the per byte arithmetic intensity is actually 3. So this is actually a pretty compute intensive workload, to be honest, right? This is a very compute intensive workload. So a lot of you might think about, well, this is like nothing. Parsing a number sounds like nothing. However, if you consider from ASCII to binary, it's more intense than matrix multiplications. Matrix multiplication is only 0.5, but this guy is actually 3, right? So, and for sorting, it's only log n divided by 4, right? So turns out that's why this is actually going to be more compute intensive. Fscanf is actually going to be more compute intensive. So you might caught me with a logic flow that, well, professor, didn't you say that this processor is slower, right? So I do agree. For Morpheus model, the problem here, I didn't say anything about improve the speed of parsing, right? And you can imagine, if you really want to get speed up, the key is not, if you revisit this formula, right? You know this part is going to be slower. So this part is going to be increasing, right? So the only chance that we can make this to work is what? Data volume has to be reduced a lot, right? Otherwise, this in-storage processing is going nowhere, right? So here is what we got, right? So if you consider the arithmetic intensity, which if you do a good job in optimizing the ASCII parsing, you can reduce the arithmetic intensity of parsing to 2. And by just having like 1 subtraction and 1 multiplication. If you can subtract everything in the very beginning, right? So this is the optimization of your arithmetic intensity. And the thing is that, how about the data volume? How about the data volume, right? So, so the luckiest thing is that, as we talked about before, right? If we want to store an integer number, for example, or a double number, for example, right? The worst case scenario, let's say for integer, the worst case scenario of an integer number in ASCII code, right, is actually 11 bytes. But for binary format, it's always 4 bytes. Do you agree with that? For binary format, it's always 4 bytes, right? So you can imagine from 11 to 4, it's actually a very significant reduction, right? So you can pretty much imagine there is a significant data reduction by 4 times, by 3 to 4 times, right? Given that ratio. So it turns out reducing the amount of communication is the way how this model would work.
We could compress the ASCII file.
You can compress the ASCII file, that is true. But then you have to suffer from the overhead of uncompressing it. And also, that increases the compute intensity on the host again, right? So that doesn't work out, right? So turns out that's how this will work, right? So here's the result we got. So the vertical axis is the speed up over the conventional baseline. And as you can see, for most of the application, we get some degree of speed up, right? And also, if you enable P2P, for some like less compute intensive applications on GPU kernels, you can see more significant speed up. However, again, sadly, so first of all, just using the Morpheus will give you 32% of performance gain. If you enable P2P, 7% more, right? So the thing is that if you have done a good job with Morpheus, then the benefit of using P2P, again, is very, very limited. And if you include the effect of patch caching, right, then P2P is pretty much like nothing, right? So although I said in the very beginning, the purpose of this paper is trying to make P2P great again. But turns out it does make P2P better, but not to the degree of greater, right? So what does that mean is that P2P is in fact an idea that's good in concept, but in practice, it doesn't work out very well if you consider the overhead that you have to pay. And even for Morpheus, it's also a very good paper in a way that the idea, you never heard about this before, right? And in the very beginning, I do have a pretty significant fight with my professor because he's like, I don't trust you. I don't trust this is a problem. And then I keep showing him Stephen Swanson. I keep showing him the data, right? Like, and I sometimes feel like this kind of question and answering, like you really want to have a red team. Sometimes you might think about why professors is always against my brilliant idea. But, you know, turns out this is the first time I have a paper that the first shot paper gets in. Because I have one of the most critical reviewer in-house. Because every week when I show him some data, he'll question me, no, this insight doesn't really motivate me, right? And then I have to keep generating more data to convince Stephen Swanson saying that this is a project that should go. Because like you, he initially would say, what if I put it in a Rendisk? And then I show him, okay, here's the result of Rendisk, right? And then what's the other incentive of doing that, right? And tell me the roof line of the improvement. So that's why I show you that in-story processing formula saying that, look, here's the potential, right? So sometimes having someone that's really critical is not a bad idea. But for this paper, I feel this is a very successful research project, but I do agree, like almost 10 years passed, you don't see people use this everywhere because there are still quite intensive programming and protocol tweak that we have to perform before it can be commercialized. So it turns out this is not a good idea in terms of commercial idea. However, research idea is a good concept to prove, right? Okay, so, but this is a real problem, right? In fact, this is a real problem, right? So commercially, how do we really deal with that problem? How do we really deal with the problem? What do you think?
If using P2P can use the cheaper material or the cheaper item for that.
Yeah, but this is not about P2P, right? The reason why Morpheus is not successful is because you still have to convert the ASCII code inside the SSD, and that needs programming, right?
After white conversion, we just
Yes, right? So here's the thing. Commercially, right? Okay, so here's the reason why people want to store data in ASCII format. Because I just have one copy of data being used by as many applications as possible. And the only reason I want to do that is because storage is expensive. That's the only reason I want to do that. But for data centers, storage is cheap because they don't use SSDs, right? And they have very huge leverage. They can get a pretty good deal in terms of storage storage cost per byte, right? So if today you are considering, and also again, data parsing, the main problem is not about your storage bandwidth, it's more about the processing overhead. So in the very beginning, if you can store data in the right format, you already win. And if your storage is cheap, it doesn't hurt that for the same data, I store it in many different formats that fits all my applications, right? So now the problem is, what if we just store them at the most appropriate format at the very beginning? So right now, I want to ask you, if you are able to define the data storage format, what are the good practices you would do? What are the good practices that you would do?
What's our goal?
Our goal is just efficiency.
Okay. Should we throw out readability?
Discuss.
It's got to be. The question is, can you make something small and analyze it? Well, no, you don't need small. If space is not a premium, then what is it for? Speed. Increase speed. Well, size would be important. You know, store it before. Well, the thing is, we're talking about data type specifically. The storage space is not premium, but the bandwidth is, right? So the size of the format does not really matter. We can only move so many bits at a given time. But we also need to configure from ASCII to serialized high computational intensity. Therefore, we either need to A, reduce the computational intensity, or increase parallelability. How to do that, that's the question.
Okay, so ideas? What do you guys think?
Just use the same binary representation.
Okay, so why?
Because then you can just copy it into memory. You don't have to parse it.
Okay, so you don't have to parse it. What does that mean?
You I guess like you don't have to. I guess you don't have to convert.
You don't have to convert.
Yeah.
So what's the benefit of avoiding conversion?
You're avoiding the problems that we were just discussing.
What's the problem we just discussed?
That you have to use a processor.
Right. So you are reducing the computation intensity.
Yeah.
Should we compress the data? What do you think? Yes? Is compressing a good idea?
If the storage chip is not, or
Right, if the storage chip is not, right? Because the whole purpose is that it spends too much time in parsing. And compression is actually also very time consuming, right? So actually, I don't know. I can probably show you one demo about that. Let me see. Can I reuse the screen? And compression. Okay. Do I have MV okay. Okay, so let me show you this, right? So here I have a code that does measures multiplication, and I'm using this LZ4 computation format, compression format to see the performance of that. So here's the code that I was originally up and running. So here, this is the version without compression. So with that, the memory copy overhead to the host is actually 57 milliseconds. And the conversion between float to half is actually 3 milliseconds. So it turns out that memory copy is the overhead here, more than the cuPlus kernel, right? So some of you might be thinking about doing compression. So for this demo, I also show that I use LZ4, which is a highly optimized GPU compression. And let's see, how does that affect the performance? So here, as you can see, the memory copy time is actually a lot faster, right? And however, if you see the compression overhead is actually very significant, right? Because previously, although you save this overhead in host to device, to compress this on the CPU, it actually takes 3.5 seconds, right? Which is the overhead you don't have to suffer in the very beginning, right? So what does that mean is that compress itself would take a lot of time, right? And here, let me check. Did I count the time of the compression? Okay, so here I think my timer should have okay, interesting. So I believe the time that I put here is actually the decompression time instead of the compute time. So the decompression time, even though it's on GPU, is still very significant. And if you put that together, that's about the same time as you send the data with the raw format. So the compression is an interesting idea, is that it may or may not help, right? So it's not something that it's something like ISP. It may or may not help, right? So compression would not be an option that people would typically consider in terms of storage. And there is one thing people would do to make the processing slower, but not for performance reason, is actually encryption. Because a lot of cases we want security, right? So that's the only reason people would do things in the storage format to make it less readable or increase the overhead of computation. But in that case, it's more about increasing the security, right? So typically, a good file format, it should be as easy to parse as possible, no computation overhead, right? And another thing is that, again, if you have assumption in some kind of algorithm applications, then you always have to store many different copies of files, right? So a good format should make no assumption to the upcoming applications, right? So also, at least it would fit most applications, right? So for example, we know database applications, they like column store, right? Then you probably want it to do column store. However, if it's spreadsheet, they probably enjoy the row store format a little bit more, right? So also depends on the data format. Like if I want to store matrix, should it be sparse? Should it be dense, right? Or it's easy for the architectural optimization, for example, caching, to work. Can it fit in a page granularity well? Can it fit to the cache blocks well, right? So those are the consideration of what's a good data format. So nowadays, here is a modern data processing stack. So we typically would have relational engines like Spark, like Cloudera, like Hive, this kind of stuff, as the engine below your application layer. And then we have different file formats like JSON, which we already talk about. It's not very efficient, right? Or another one like Paquet, which is a very popular format long time ago. And also at the back end, you would have Hadoop HDFS or Amazon S3, this kind of cloud storage, which is typically some kind of object storage to store your data, right? So each object is pretty much like partial part of the, it's pretty much like a file. So let's talk about Paquet first, because Paquet is probably by far one of the most popular cloud storage format. So if you look at this Paquet format, this is what it looks like, right? So first of all, it's designed in this way. So for each single Paquet file, it's a hierarchical design that you have a row group. And the row group could have various sizes, like different columns. Different rows. And each row group, they can store different number of columns. Right? You can see that Paquet is something that they recognize that, okay, some applications, they want row store, some applications, they want column store. So I try to make my storage format not either preferring column store or not preferring row store, right? So that's the format they design. And this format is designed more than 10 years ago. So 10 years ago, you guys were born, right? So more than 12 years ago, right? You guys were born. Can you remind yourself between now and 12 years ago, what in computer system has changed? This is a hard question.
I was only 12, so.
Not yet. That's way too early.
That was like 2 cores a bit more.
Starting.
Yeah. Everyone using IE. Everyone knows stuff. Yeah, but compared to now versus then.
Okay, what has changed? It seems like a hard question. So let's brainstorm together. At 2013, what's difference? What's different? Windows XP to Windows 11. Okay, what else? Windows 11. What else?
We were talking about how like there were like less cores still, and it was just starting out like in 2013. There was like just starting to experiment like commercially with like multi-core systems.
That's actually not the last decade thing. That's two decades ago, right? So, but we do try to have more cores, right? Why is that? Single core performance doesn't improve anymore, right? So one of the things that's worth mentioning is that CPU performance is pretty flat in the last decade, right? So in the past, a lot of people in the past, people don't think ASCII to binary is a big problem. Because that was a period of time that people would believe one day processor will help us address that issue, right? So they don't think ASCII is a big problem because they think CPU can go faster and faster, right? So one thing has changed, right? CPU is not getting any faster. What else?
Memory was a lot more expensive.
Really?
Well,
at 10 years ago?
Not more expensive in the sense, but like I don't remember ever hearing about like 32, 16 gigabyte RAM sticks back then. People were still on 2, 4, 8.
Okay, so memory gets larger. What else? You have more cloud computing. Okay, so what's that make difference? What's the difference between cloud computing? What? Remote I/O. Okay. What's the other thing about cloud computing? Distributed. Okay, so with distributed system, then what do you also use? Network. Okay. Software layer. Software-wise, what do you use? How do you store data? Or what kind of data do you typically form? No. Well, beyond that. So I don't know if you guys have read these papers in your operating system class. right? The file system is also changing. Like either Google file system or Facebook, they prefer append and also larger chunks of accesses, right? So the file system itself also changes. In the past, we are more block-based, but right now it's more segment-based. And each segment is become larger and larger, right? What else?
Isn't the CPU and memory performance gap still increasing?
CPU and performance gap still increasing. CPU and memory performance gap. Well, I would say that would probably remain the same, right? Because you are consider CPU is not getting any faster, right? And the memory is also like that, right? So the CPU performance and memory performance gap is not really changing a lot. But given if you have larger file chunks, what does that mean? You need bigger storage? No, you need bigger cache, right? For example, if right now each chunk of your file is like in Google file system, it's 64 megabyte, right? And for some of the other file systems, they go up to 128, right? So for example, if you have 128 megabyte of file chunks to cache, in the past, if it's just 5 blocks, right, it's only like 5 times 4 kilobytes. Sorry, 8 times 8 blocks, then it's only 8 times 4 kilobytes, right? That's only like 32 kilobytes. It fits in your cache perfectly. But right now you want like gigabytes of cache to cache everything, right? So that means that your CPU cache performance is going to be really bad, right? So that's one thing changed. What's the other thing that we have, but in the past we don't have? Actually, don't forget about this, right? You have multi-channel SSDs, right? So in the past, people design file formats with large chunks because they think things are going to be in hard drive. So they want to form as many sequential accesses as possible. But today, if you have solid state drives, actually you want data to spread out as evenly as possible. So it turns out small random access isn't slow, is not that slow anymore, right? So those are the things that we have changed. First of all, the CPU performance versus I/O, right? That gap is actually shrinking. And sequential I/O versus random I/O is going to be also like the performance difference is going to be shrinking as well, right? And a lot of you saying that, well, because it's cloud, so remote I/O actually becomes more important, right? And also, like in cloud storage, metadata lookup, that's an issue, right? So also in the past, when we write a program, typically it's just the direct C program running on your computer. But the software stack nowadays, you don't directly run this application. In fact, there are a lot of other software stack. It's either Python runtime or the Hadoop runtime, right? So turns out there is a very huge overhead between this whole things together. So here is another graph that's similar to what I showed you before. The vertical axis is the throughput in gigabit per second. And the horizontal axis is different file format. And JSON, as we mentioned, and also this is gigabit per second. So if you want to convert it back to bytes per second, you have to divide it by 8. So what does that mean is that like 2.8 divided by 8, right? So it's only like 0.3 something, right? So it's 350 megabyte per second, right? So And the reason, again, as I said, JSON is based on ASCII, so that's why it's so slow. And like Parquet format is a very popular format. It's still like 12.5, less than one, just about like 1 gigabyte per second, right? So it's very inefficient. Even with ORC or Arrow format, they are still way slower than the NVMe performance at the time that this paper has been developed, right? So turns out this paper that we talk about right now, they are developing this LBIS format. So the LBIS format is a file format to store relational data tables for read-heavy analytics workload. So again, this is read-heavy, not for writes, right? So if you're talking about writes, there is nothing that could beat like sequential append, right? But again, if you think about you are going to design a data format for a relational database workloads, then it's a format that has to support basic primitive types in frequently used database format. So like, for example, it supports integer, supports double, supports a varchar, this kind of stuff. And they make a few design decisions. So first of all, they try to avoid the CPU pressure. So for example, no encoding, no compression. And simple metadata management on distributed storage and carefully managed runtime. So if you take a look about their design of their file format, instead of row group, they also introduce another concept called column group. So it's more like a two-dimensional design in data partition. So in this way, they can better support column formats. Because as we mentioned, a lot of relational database, we prefer column access more than row accesses. So in this kind of design, they still have the row group concept, but they put more columns within. They emphasize more columns by using column groups. So instead of just having a few columns, they can access more columns at the same time. More elements within the same column at the same time, right? So that's their design. So if you are interested, you can take a look at this paper a little bit more. And as you can see, with the improvement of file format, you don't have to modify anything, just the file format. It will give you double up performance, right? So if you are interested, go read this paper. And we are running out of time. So, and since the next lecture, we have to spend half amount of time like having your final presentation. So I'm not going to talk too much more about the course material for today. And if you're interested, just go read that paper. And on the next lecture, I will wrap up with what we have learned with system design perspective. But a few things. First of all, evaluation is open, so give us good reviews. And also, here's what we expect in your final presentation. Other than that, enjoy the rest of your day. I will see you in the next lecture.